Okay, so about today's lecture, let me say that this one is perhaps one of the most important lectures in this series, because we are going to develop the fundamental notation and workhorses of quantum computers, which are different gates and how they act on qubits, and how we work with them, how do we represent them, and how do we see that, how to analyze the effect of different gates on different states of qubits. After this, we will mostly be concerned with different types of algorithms. So even if you don't get one algorithm, you will be able to get another algorithm. So most of the lectures after today will be sort of independent from each other, but they would all be based on the notation and algebra that we will develop today. So please pay attention, and if you have any trouble, I would be happy to talk about that, or maybe give another example of that step, or explain it differently. And also, at the end of this lecture, I will again introduce some new functions and notations in Jupyter Notebook, that the gates that we will study today, we will again see how to work in Jupyter, and what are the commands and codes to implement those gates. So, but that last part is actually not that important today, as the first part is, which will make us familiar with different types of gates. So let me start sharing my screen. Okay. All right. Okay. So during this session, my focus is actually always on my writing pad that I have, where I would be writing. So I will not be, unfortunately, be able to look at the chat. So Mosana will be looking at the chat. But if there is something that is not being addressed, and you see that I'm passing through it quickly, you can just unmute yourself and please ask a question. Most likely, if you're having trouble, somebody else would also be having trouble, because almost all the people in this group are not doesn't do not have a physics background. Okay, so let's begin. And before I begin today's session, let me quickly give a summary of sorry, let me close all of the applications. Okay, so let's just review the key points that we will uh, need today and later on. So the first thing is this, that quantum computers are, if you just want to get a summary of yesterday's lecture, even if you forget everything, you need to remember a couple of things. One thing is this, that quantum computers are essentially different operations on a two-level quantum system. Physically, there are more levels, but we are just concentrating on two of them. And the workhorse is a qubit, which we can represent, uh, let's say, as a superposition in general of two states, 0 and 1. And we can label the lower state as 0 state and the upper state as 1 state. So in general, our system is going to be in either 0 state or 1 state, or a superposition of these two states. And the when a system is in a superposition state, when we measure it, it's either going to be found in 0 state or 1 state, with a probability of being found in 0 state is a modulus square, or absolute a square. A is a complex number, and probability of measuring 1 state is b modulus square. So this is sort of a summary of yesterday's lecture. And to make sense of everything, it's important that sum of these two probabilities is 1. That is, our state is normalized, so to say, which means that a modulus square plus b modulus square is 1. So this is something that we are always going to make sure that the states are normalized. And operations on these qubits, which we will now mostly call gates, so that our formalism is similar to classical computing, where we had those gates through which information flows, and gates represent logical operations. So these physical operations, we will be calling them gates. They are unitary operation. A unitary operation is an operation, if we think of it in terms of matrices, is this, that the inverse of this matrix is just given by its complex conjugate and transpose. So this dagger symbol or cross symbol, this represents conjugate and transpose, which means that if we multiply this matrix U with its complex conjugate, we should get identity. And we can see that this unitarity preserves uh, this probability. That if, for example, if there is some qubit which is in state psi, and we perform some unitary operation U or gate U, and it goes to some state psi prime, which is symbolically written as this, that this means that U operated on psi, or you can think in terms of gates, that U psi means that psi has passed through gate U. So if this is this, and if I want to compute the magnitude of this psi prime, I have to multiply this psi prime ket with psi prime bre, and the bre psi is nothing but uh, complex conjugate of psi ket psi, and let's multiply it with this. And this psi prime is u psi. So when I take this dagger of this becomes so this, when this conjugate transpose is brought to these two matrices, they change their place, and we get this psi prime. And now I can, so this dagger, when it comes to psi, so psi dagger is psi bra. When you take the conjugate transpose of this psi ket, it becomes psi bra. And when you take the conjugate transpose of u, it is just u u dagger, which is the conjugate transpose, because u is still arbitrary, but their places are also shifted. You might remember from this, when you have some A, B matrices, their uh, uh, their complex conjugate transpose products is the in the reverse direction. So let's put the value of this psi prime as well, which is u into psi. So this u dagger into u, because u is unitary, so this u dagger is u inverse. So u inverse into u is identity. So this goes away. So this means that because this u was a unitary operation, after this operation, psi prime still has the same magnitude square as psi. So it means, so since this was normalized, this psi state, so it means psi prime is also normalized. So here I showed that if U is unitary, this operation preserves the probabilities. We can prove inverse as well in general, but we'll have to go to more computations, and you can take my word for it, that if we start by assuming that psi prime is normalized, we will end up finding that U should be unitary. So both ways, if U is unitary, psi's probabilities are preserved, which means the total probability is 1. And if we start by assuming that psi prime's total probability is 1, we will end up with U as a unitary operation. So this is one thing. And for one qubit gates, this U matrix is a 2 by 2 matrix. Let's call this symbol 2, 1, 2, 2. So this U is a 2 by 2 matrix because our State is also a 2 by 1 matrix. So in general, this state psi AB can be written as a column vector AB. So since this is a 2 by 1 matrix, any operation on this can be represented by a 2 by 2 matrix. So if this U is this, it means that U dagger should be A11 conjugate, A21 conjugate. We will take its conjugate, and we also have to take transpose. So this goes there, and its conjugate transpose, its conjugate is placed here, and A22's conjugate. And we can check one thing quickly, that if U dagger and U has to be identity, we can see a condition immediately. So U dagger was A11 conjugate, A21 conjugate, A12 conjugate, A22 complex conjugate, and U is A11, A12, A21, A22, and this has to be identity. So if I use the rules of matrix product, so I get A11 star plus A21 star, A21. So this multiplies with this, and this multiplies with this. And similarly, this row gets multiplied with this, and we get A11 star, A12 plus A21 star, A22. Similarly, this row gets multiplied with this column, A12 star, A11, A22 star, A21, and this row gets multiplied with that. A12 star, A12 plus A22 star, A22. Now, for this to be an identity, it means that this term has to be 1, and this has to be 1, and these two has to be 0. So let's see what this is. This is nothing but A1 absolute square, and this is A21 absolute square. So this has to be 1. Similarly, this gives us that A12 absolute square plus A22 absolute square has to be 1. So it means whenever we write this unitary matrix to write our gate U, we have to make sure that the absolute squares of the columns add to 1. So A11 mod square plus A21 mod square is 1. A12 mod square plus A22 mod square is 1. We also have to make sure of these conditions, but these are, a little bit clumsy to check. But this is the first check that we should always make, that whenever we prescribe a gate, that does this condition fulfills or not. So if this doesn't fulfill, it means it's not unitary, it's not a legitimate gate. Okay, so with this thing, let's now start with few examples of different gates. And one of the fundamental gate that we have is the X gate, or more precisely, it's mostly called Paulie X gate. It resembles the classical NOT gate. Classical NOT gate, if some of you are familiar, what it does, it converts bit 0 to 1 and bit 1 to 0. So this is sort of the same gate. And it's called Paulie because its matrix resembles a Paulie matrix in quantum physics. So this Paulie X gate is defined to be something like this, that it transforms state 0 to state 1 and state 1 to state 0. So we need to find this, the unitary matrix for this operation. And just to remind you that cat 1 is 0, 1, and cat 0 is 1, 0. So we need to find a matrix that does this operation, that when we multiply with 0, it goes to 1. When we multiply with 1, it goes to 0. And the matrix is this. I'm just stating it, and we can just check that it really does this. So this matrix does this job. And let's check. So to check it, let's see if I multiply this X with 0. What I mean is this: the 0, 1, 1, 0. Let's say what we get if we do this matrix multiplication. So 0 into 1, 0, plus 1 into 0, 0. And the bottom row multiplies with this again. So 1 into 1, 1, plus 0 into 0. So this is 0, 1. And this 0, 1 is nothing but ket 1. So you see that when this X gate is applied to this state 0, we get 1. So by the way, some people also represent it with sigma X, simply because of convention in quantum physics, where this Paulie X gate is represented with sigma X. But I will be using this X symbol. This is a little bit, cleaner. Okay, so similarly, you can check that if I multiply this X gate with 1, I get this, which is 0. So it means that 0 goes to 1 and 1 goes to 0. So this is very neat and clean. So what happens to a superposition state? For example, if I have a general psi, what it does to that. So before that, let me just quickly show you what happens in the block sphere, because it's helpful to picture. So if x, y, z are our axes, so what happens is that if we have a state 0, this goes to state 1 after Paulie X. And if we have a state 1, when we apply it, this goes to state 0. So it's sort of 180-degree rotation because we move from one side to the other side. Even though right now the axis is hard to specify that what axis does it rotate around. But we can quickly see that. So how, for example, if I write my state psi as some A0 plus some B1, and the action of this gate X on the state psi, I can specify like this. So this X will distribute. So this X0 plus B X1, and X on 0 turns it into 1, and X on 1 turns it into 0. So if we have a superposition state A0, B1, it goes to A1 plus B0. And to visualize it on the block sphere, let me start with this normalized state psi that we discussed yesterday, that in general we can write our state psi, normalized state psi, like this: sine theta by 2, 1, where this theta is the angle of this qubit. If this is the state psi, so this theta is the angle with z-axis, and phi is the angle of this projection in the xy plane with the x-axis. So let's see what happens when we apply x gate to this. So when I apply x to psi, I get cos theta by 2 as it is, and when x goes to 0, this becomes 1, and exponential iota phi sine theta by 2, and when x applies to 1, it becomes to 0. And let me rearrange this stuff a little bit. So if I take exponential iota phi common, so I get sine theta by 2, 0, plus cos theta by 2 into exponential minus iota phi 1. So what happened? When I took exponential iota phi common, there's no exponential iota phi with the cos theta by 2, 1. So I put exponential minus iota phi. And this sine theta by 2, and I just write this thing later and this thing earlier, so that it looks sort of similar to this thing. But still I have cos here and sine here, which I can easily take care by recalling that sine theta by 2 is nothing but cos theta plus pi by 2 into 0, and this cos theta by 2 is nothing but exponential minus iota phi sine theta plus pi over 2 into 1. But this actually gets with negative sign, so I will have to put a minus sign here. But this minus, I can write it as exponential iota minus iota pi. The minus 1 is equal to exponential minus iota pi, which means that we can combine the powers of these two exponential as phi plus pi sine theta plus pi by 2, 1. So if I compare it with the original state, so we see that I can ignore this global phase. As we discussed last time, that when we try to find the probabilities, the global phase factors out. And if I compare angles, so this state psi that had angle theta with z-axis has now angle theta plus pi. And this angle phi that was there with z-axis is now angle pi plus phi. And it means that if I now draw it on the block sphere, what happens is this. So if there is a state, general state psi, which has angle theta and angle of the projection phi, after the operation, this goes to a position where theta goes to theta plus pi, which means the state is gone to this side, and angle phi also increased by pi, so it has to be on this side. So which means that its projection now will be making angle phi plus pi on the other side. So it means this state that was here has now gone to the opposite side. And just for example, if there was a state in the x, if this was a state in yz plane, after operation, it still remains in yz plane because this phi was 90. So if I add 270 to this 90, this becomes 370. So this still remains xz plane. So this is as if the state has been rotated around the x-axis. So this is x-axis. So the state is rotated around the x-axis by 180 degrees. So we can, remember the general operation of this gate X as rotation around x-axis in block sphere, on block sphere by 180 degrees. So this is the general action of this gate. So this also tells us another important thing, that our state plus, let's use this color, our state plus, which is along x-axis, and our state minus, which is along y-axis, will not be affected by this gate X. And we can explicitly check. If I apply X gate to plus state, so plus state is the superposition of 0 and 1. So when this X goes inside, this 0 becomes 1, and this 1 becomes 0. So I can rearrange it again. I can write it 0 plus 1. So this is again plus. So X gate does not change the plus state. Similarly, if we apply X gate on minus state, we will see that except for a global phase, the state is the same. So this X goes to 0 and makes it 1 and makes this 1 0, and I take negative common. So minus 1 over under 2, 0 minus 1 is minus minus. So except for this global phase, this state minus remains minus. So it means that this plus and minus states are the eigenstates of this operator X. So that's why this plus minus, when we express our general state psi as a superposition of plus state and minus state, we refer to this plus minus as X basis. And this X, this plus and minus states are X basis simply because they are eigenstates of the X operator. Okay, so let me take a stop here and ask if there are any questions or confusions around the X gate. This is one of the most widely used gate in quantum computing.
Assalamu alaikum, sir. Madiha here.
Walaikum
So just wanted to confirm that you just iterated that in Paulie X gate, the phi angle takes an increment of pi. Can you reiterate that? What is the increment in theta angle?
So it's actually in theta. So there's a change both in theta and phi. But
Yes.
this phi that we remember it as, this is by the amount by which the state rotate around the x-axis. So that rotation around x-axis would change both theta and phi.
Yes, but phi is taking a change of 180 degree. That is why the projection of the result of X gate is pi degrees greater than the original qubit. So I was asking that what is the change, specifically change in angle of the qubit, a theta change in angle after the X is
theta changes by 180 degrees.
180 degrees pi. Thank you so much, sir.
Thank you. Okay, so let's now move on to the next very important gate, and this is Paulie Z gate. And this is a very simple gate. What it does, that it converts bit 0 to 0, that it does nothing to 0. But when it operates on bit 1, it multiplies it with the phase factor -1. So it adds a 180 degree phase, sorry, not the minus, but this, the state remains 1, but with a minus sign. So this Z gate can be represented by the matrix 1, 0, 0, -1. And we can check quickly that if I apply 1, 0, 0, -1 to this 0 bit, which is 1, 0, when I multiply 1, 0 with 1, 0, I get 1, and 0 -1 into 1, 0 is 0. So this is again 1, 0. And when I multiply 1, 0, 0, -1 to 0, 1, I get -0, 1. So this matrix that I have written here, 1, 0, 0, -1, this does this job. So it means if we have a general state psi, A0 plus B1, when we apply Z gate, and some people, by the way, write it as sigma Z, but we will simply be writing it Z. When this Z applies to psi, this state becomes A0 minus B1. So this one ket gets a minus next to it. So let's try to see that what it does to a general state. Okay. And just before that, let me quickly see what happens to this plus state. Okay, so for basic gates, it's better to work out both for 0, 1 and plus minus, just to get some intuition to how what this gate actually does. So when we apply the Z to this plus state, which is 0 plus 1, so the 0 remains 0 and 1 gets a minus sign. So this is nothing but the minus state. So this Z gate basically changes plus state to minus state. And let's see what it does to minus state. So when Z applies to minus, so Z is 0 minus 1. So when it applies here, we effectively get plus state because this minus sign becomes plus, and we now have plus state. So this is a very nice gate. So this is essentially a NOT gate, but for plus minus basis, for the X basis. If you're working in the X basis, and X basis means that your basic states are plus and minus states. So this essentially works as a NOT gate for the X basis or for the plus minus basis. So the plus state goes to minus state and the minus state goes to plus state. Let's now see what it does to a general superposition state. So Z applied to this general state cos theta by 2 plus exponential iota phi sine theta by 2 1. So fortunately this time this 0 remains 0 and this 1 will get a minus. So exponential iota phi sine theta by 2 1. But this minus I can write it as exponential iota minus iota pi, pi by 2. No, pi, because when I expand exponential minus iota pi, we will get cos pi, which is minus 1. So this minus 1 is exponential minus iota pi, and so I can write this state as cosine theta by 2 plus exponential iota phi minus pi. And by the way, I can also write it plus pi, iota pi, because it doesn't matter. Cos pi is minus 1 anyway. So for simplicity, let's write it plus pi sine theta by 2 1. So now we see that for a general state, if I draw a block sphere here, x, y, z. So if we have a state psi that has an angle theta and its projection has an angle phi with the x-axis, it doesn't change theta this time. It only changed phi by pi degrees. And it means that if we have a state here, this state goes to this side such that its projection now has an angle which is phi plus pi by 2, but theta remains the same. So it means that this is a gate which rotates a state around z-axis. So this Z gate rotates the state around z-axis by angle pi. So there's a simplicity, with all of these gates that fortunately the things have been worked out in such a way that it's very easy to remember. X gate rotates a state around x-axis by pi degrees. And I don't have to say if it rotates clockwise or anti-clockwise, because the total degrees on a sphere are 360 degrees. So 180, if you go this way or that way, it's the same thing. So we won't be saying clockwise or anti-clockwise. That's why you might have seen that I didn't pay attention to plus or minus sign that was appearing here or here, because it doesn't really matter. But it doesn't change theta. So it means the Z gate rotates the state around z-axis. And you have also noticed that this 0 and 1 states are the eigenstates of this Z gate, because 0 goes to 0 and 1 goes to 1 with just a global phase minus. So it means that this 0 and 1 can also be referred to as the Z basis. So the 0, 1 is the Z basis, simply because these are the two states that are the eigenstate of Z operator. By the way, we also have another name for them, computational basis, that we introduced yesterday. And plus minus are the X basis, because they are the eigenstates of the X operator. Perfect. So now I have introduced two gates, and there are more gates. And somebody actually yesterday asked a question about reading for this thing. So today I will also introduce you to a web page. Actually, this is just Qiskit.org. So you can go there. It has helps with the code and also with these basic gates and their matrices, etc. Okay. So anyway, the next gate that is important is the Y gate, and this has this matrix minus iota 0. Now I'm not going to do any derivation. I can leave it as an exercise for you. So this is equivalent to pi degree rotation around y-axis in the block sphere, and the state plus I and minus I are the eigenstates of this operator, where plus I state is 0 plus iota 1 and minus I state is the 0 minus iota 1. And by the way, this Z matrix can also be written as minus iota x into z. So if you multiply z into x, z and x, and multiply with minus iota, you get this, sorry, not z gate, but this y gate. So this y gate can also be written like this. So this z gate that we refer to as phase flip gate, because it adds a minus sign to one state, and this x gate that people generally refer to as the bit flip gate, because it turns 0 into 1 and 1 into 0. So this y gate is a bit and phase flip gate. So it does both things at the same time. All right, so I have more gates to discuss later on, but before I do them, I want to introduce another part of the Roch notation. And even before I do that, let me just give one state that why these x, y, and z gates are important from another point of view. If you include identity operation in this group as well, so these four metrics actually forms sort of a basis for any general unitary, because any general unitary matrix U that is like 2 by 2 matrix can be written as a superposition of these four gates. I'm not going to prove it, but it's very easy to understand as well. These X, Y, Z, and I gates, they are orthogonal, they are independent of each other. You can't construct one from the other. And since this is a 2 by 2 matrix with four parameters, you have to have four sort of basis matrices. Even though there's a condition on this unitary matrix that it has to satisfy, it is unitary. So there is a condition on these parameters A, B, C, D, etc. But in general, we can express any general single qubit gate as a sum of X, Y, Z, and identity gate. So they're important in this respect as well. Okay, so, but before I introduce two more gates which are important, let me introduce one very important concept in Darach's bracket notation that we are using so far. Some people write with this dash, but you can also write it as it is, bracket notation. And that is a concept of outer product. So previously we had inner product. So inner product of two states. For example, if you have psi1 and some psi2, the inner product is simply you convert one into bra and keep other as ket, and then you evaluate this inner product. For example, if the psi1 was a1 a2 and this psi2 was b1 b2, this inner product of psi1 and psi2 is that you first prepare a bra from psi, and the bra from psi means that you take its complex conjugate transpose. So this becomes a1 star a2 star. So this row, this column vector becomes a row vector and also conjugates of its elements, and then b1 b2 as it is. So this becomes a1 star b1 plus a2 star b2. So we get one number after inner product. So inner product is easy. You convert like two column vectors into a single scalar number. And we also find the magnitude square of any vector from this as well. If you make both of these psi1, psi2 equal, so mean a1 is equal to b1 and a2 is equal to b2, then this is just a magnitude. So this inner product is a scalar product. But this outer product is different. This is like that we had, the place of this bra and ket in the opposite spaces. So here, bra is on the left and the ket is on the right. So this becomes a bracket. So here it's a ket bra. So ket is on the left and the bra is on the right. But it works out in the same fashion. So this psi1 is a1, a2, and this psi2 is now a bra. So this becomes B1 star, B2 star. And this is going to be a matrix because I multiply this row with this column. So this is A1, B1 star, first number. Then I multiply this row with this column. So this is A1, B2 star. Then I multiply this row with this column. So this is A2, B1 star. Then I multiply this number with this B2. So this is A2, B2 star. So we have converted these two column vectors into a 2 by 2 matrix. So whenever you see this, outer product, this is always a matrix. This is a square matrix. If these psi1 and psi2 states have the same number of elements in there to represent them. So this thing, is very helpful. For example, if I have in outer product of 0 and 1 like this is nothing but 0 state is 1, 0, and 1 state is 0, 1. So this 1 into 0, 0, 1 into 1, 1, 0 into 0, 0, 0 into 1, 0. So it means this matrix 0, 1, 0, 0 is equivalent to this cat prime. Similarly, if I have 1, 0, so 1 is 0, 1, and 0 is 1, 0, you multiply them, you get 0, 0, 1, 0. Okay, so somehow screen sharing was stopped. Okay, and unfortunately, I don't know if the notes that we had are lost or not, but let me start journal again. Okay, so it looks like what we wrote is all lost, but no problem at all. We'll continue. So let me just quickly write this thing. We had worked out 0, 1 as 0, 1, 0, 0, and similarly 1, 0 as.
I think you need to share your screen. You cannot see it.
So apologies for that. Sometime it happens that this software crashes, even though this is from Microsoft and this computer is a Windows computer. Anyway, so okay, can you see it?
Yes, we can.
Okay, so this 1, 0 becomes 0, 0, 1, 0. Similarly, this 1, 1, if we write it, this is 0, 1 into 0, 1. So this becomes 0, 0, 0, 1. And if I work out this 0, 0, this is 1, 0, 1, 0. So this becomes 1, 0, 0, 0. So you see, first of all, we have a very nice thing that this 0, 1 is a matrix with only 1 here. This 1, 0 is a matrix with only 1 here. Similarly, 1, 1 is a matrix with 1 here, and 0, 0 is a matrix with 1. So it means that I can represent a general 2 by 2 matrix with this notation. And let's try this thing with the X gate. So X gate was a matrix like this: 0, 1. Let me see if so 1, 0. This was X gate. So it means I can write it like this: 0, 1, 0, 0 plus 0, 0, 1, 0, right? If I add them again, I get back this matrix. But now I can do one more thing. This 0, 1, 0, 0 is nothing but a representation for, let's see, 0, 1, 0, 0 is for 0, 1. So it means that this is 0, 1, and this 0, 0, 1, 0 is 1, 0. So it means I can represent my operator X or the gate X in Dirac's bracket notation as well instead of matrices. So this 0, 1 and 1, 0 and their addition, this represents this X gate. And this actually is even easier to work with. And that's why people like this notation a lot. You see, I can now work out operations of this matrix on different qubits very quickly. For example, if I want to see what happens when I apply this X to 0, I have this thing 0, 1 plus 1, 0. So multiply with this state. So now this comes and multiplies with both. So when it multiplies with this one, this is 0, 1 into 0 plus 1, 0. Somebody trying to ask a question? Okay, no. So if now let's see, this is 0 because 1 and 0 are orthogonal. So this goes away. And this 0, 0 is 1. So I'm left with only 1. Okay, so because this is written nicely in a way that 0 on the left and 1 on the right, and 1 on the left and 0 on the left. So it means if 0 comes from the right, 0 multiplies with the 0 gets 1. So this 1 comes here. And 0 multiplies with 1, it is 0 because they are orthogonal. So this goes away. So this part goes away. Similarly, you can see that if I bring this one state from the right, 1 into 0 would be 0. So this will go away and we will get 0. Similarly,
sir, I have a question. Okay, all these operators, applying operators on any qubit is fundamentally we can visualize it as a rotation in Bloch sphere. So can we introduce quaternions as a point on Bloch sphere and all these operators as a specific quaternion number? And when we, instead of multiplying two matrix, we just multiply two quaternion number to have three-dimensional rotation. By this way, we could, reduce our calculation from matrix multiplication to number multiplication.
So actually, the quantum mechanics in this two-level system and the states require like 3 parameters to represent them, and there are more than one ways to set up the math and show all of these operations. This 2 by 2 matrix approach is perhaps one of the easiest one because most of the people are familiar with them in their high schools. So I think that's why this is a bit easier for most people to work with. Otherwise, you're absolutely right. There are more than one ways, and some are more difficult to visualize than others.
I was asking because I think it could be computationally fast or efficient. Because
I'm not sure because the math that we are developing has nothing. It's our own construct that we are trying to understand what is happening. But physically in the hardware, whatever is happening, that is independent of the math, and that should be.
No. Actually, I'm talking about when we simulate these operators. So if we just use quaternions, then we could, in simulation, we could just multiply those two quaternions instead of matrix multiplication.
Okay. For simulation purposes, yes, there are ways to speed up the simulation because these matrix multiplication that can be costly when we go to high qubit.
Sure, sir. Thank you. I was just confirming.
Okay, thank you. So let's now see how we can express this Z gate, which I wrote as 1 minus 1 0 0. So we can write it as this 0 0 0 minus 0 0 0 1. So this one is nothing but 0 0, and this one is nothing but 1 1. And we can now see the operation visually very easily as well, because if I'm going to multiply this Z with one state, and when this 1 comes from this side and operate on this operator, when this will be multiplying with this thing, this 1 into 1 will be 1, and I will get this minus 1. Because this 1, when it goes to this part, 0 into 1 would be 0, because 0 and 1 state are orthogonal, so this will go away. Similarly, when this Z applies on 0, and this 0 applies to this operator from the right side, 1 into 0 would be 0. So this term goes away, and 0 into 0 is 1. And so I get 0. So this also has a benefit that I can write actually this operator directly. If somebody would have asked me to find an operator, find a gate, and let's say in this bracket form or matrix form that does this, that 0 goes to 0 and 1 goes to -1, I would have directly written this state, because this term 0 into 0 guarantees that when 0 comes from right, 0 will go to 0, because 0 into 0 would be 1 and I will be left with 0. And when 0 multiplies with this one, 1 into 0 would be 0. So this term will not have any effect. But when 1 comes, when 1 will come to this thing, 0 into 1 will be 0. So this term will have no effect. But 1 into 1 will be 1, and I will be left with -1. So this bracket notation has this advantage that it's very easy to visualize. So I can write this operator form directly. Okay, so any question about this bracket notation? This is actually very important, because that's what we are going to use from now on for most of the time for operators. For example, let's now talk about this very important Hadamard gate. Perhaps.
I'm sorry to interrupt you. Can you just tell us the same notation for the Y gate as you have told for X and Z, the outer product notation?
Okay, so Y gate is iota 0, 0, minus iota, if I'm not mistaken. Sorry, iota goes on the other side. So this gate is Y minus 0. So iota minus iota 0. So you see, this is iota is in place for 0, 1. So I can write it directly. Iota is. So let me see if I wrote this Y gate correctly. So Y gate, okay, so minus sign is here. So this is Y gate. So this iota is in place of 1, 0, and this iota is in place of 0, 1. So this is going to be the symbol for this Y gate for operator form. Okay.
Thank you, sir.
Okay, perfect. So let's now go to this Hadamard gate. This is an extremely important gate. 1 over square root 2, 1, 1, 1, minus 1. And you can now see that I can write it in bracket notation very quickly. There's a 1 at every place, so it means all the 4 basic brackets, the cat bra products are going to be here. So this is 1, so I will have 0, 0. This is 1, so I will also have 0, 1. So this is 1, so I will also have 1, 0. So this is minus 1, so 0, 0. So 1, 1 will come with minus 1. And when it does to different qubits, we can easily see. Let's see what it does to 0. I leave it as an exercise for you to convince yourself that if I do it in matrix form, we will arrive at the same thing. But when I apply this h to 0, let's quickly work out. When this 0 multiplies here, 1 into 0 would be 0. So this term is 0. So when 0 multiplies here, 0 into 0 would be 1. So this plus 1 cat will come here, because 0 into 0 is 1. So when 0 multiplies on the right side of this thing, this is 0. So this comes to 0. And when 0 multiplies here, 0 into 0 is 1. So this 0 comes here. So it means my state is 1 over under root 2, 0 plus 1, which is nothing but plus state. So this Hadamard gate is very important, because it can convert your 0 into plus state. And similarly, if you apply this Hadamard to state 1, it goes to this minus state. And this gate is actually important for other reason also. It is very easy to implement physically. Physically, if you have a two-level system with, let's say, with an energy gap h nu, if you just send an optical pulse or electromagnetic wave, which has a frequency nu, but you send it for only a duration which is equal to half of the time period of this pulse, that pulse actually prepares a superposition state. If the system is in ground state, it goes to a superposition state with the plus sign, and if the system is in the upper state, it goes to a superposition state with the minus sign. So this is one of the oldest way of preparing superposition states of these two things, and it's very easy to implement physically. So this gate is not only important logically, because 0 goes to plus and 1 goes to minus, but it is also very easy to implement physically. So that's why it's almost an integral part of most of the quantum algorithms that we will study in this course. Okay, so before I introduce another gate, let me note one important property of these gates that I unfortunately haven't been able to address before, is this: that when X is applied twice, we get an identity. And this should have been apparent from the properties of X. Remember, X rotates by 180 degree around X-axis. So if I apply X again, I should rotate total by 360 degree. It means I should get back to the same state. Similarly, the Y gate, when it is applied twice, it results in identity, because this is a rotation by 180 degree around Y-axis. So if you rotate by 360 degrees by rotating it twice, you should get identity. Similarly, Z square is 1. This Hadamard gate actually shares the same property as well. If I apply Hadamard gate twice, we get identity. And we can easily check. For example, this Hadamard applies to 0, gives us plus, and I checked it with this operator form. I encourage you to check it yourself as well, that if we apply this Hadamard gate to plus state, it goes to 0. So if we apply Hadamard to minus state, it goes to 1. So it means that Hadamard square is also an identity. Though not all 2 by 2 gates are identity, but these fortunately happen to have this property that if you apply these gates twice, you get identity. So this is something that we exploit a lot in the quantum algorithms as well. Okay, so any questions regarding these gates?
I'm extremely sorry for asking too many questions. I have a comment and okay, I have a comment and a question. So can we say, or as you said, that X squared, Y squared, Z squared, and H squared all correspond to identity. So can we say that all the unitary matrices, the squared of all the unitary matrices always give identity? Can we say that?
No, we can't.
Okay. And the second question is that, as you told, that X, Y, Z, and identity are sort of the basic operations that through the superposition of those we can form any gate. So can you elaborate the expression of superposition which can give the Hadamard gate?
Yes. So
which can give us an output as a Hadamard gate.
Yeah, it's very easy. So if we look at Hadamard, which is 1, 1, 1, minus 1, I can write it as 1 over under 2. So let's say, so actually it can be written as X plus Z. And we can see this X gate was defined as 1. This X gate was 0, 1, 1, 0, and this Z gate was 1, 0, 0, minus 1. So if I add both of these, I get this matrix. And we can, of course, multiply with 1 over under 2 here, 1 over under 2 here, and we get this 1 over under 2. So we can quickly see that Hadamard gate can be simulated as sum of 2x and as sum of X and Z gates.
So is there a formal method to calculate this? Because if I want to find the superposition combinations of, for example, S gate or T gate, I'll have to, do I have to try the, use the hit and trial method, or is there any defined method for,
No,
finding this
actually,
expression?
no, you can have a systematic way, because all you need is start from, okay, sorry, I think that equation has gone away. So some unitary a x plus by plus cz plus di. So you put your unitary here, and then x, y, z, I are known. You put it here. From here, you get four equations, because there are four numbers on both sides. So equate left side, right hand side, and you have four equations and four unknowns. You should be able to solve for these a, b, c, d.
Okay, so sort of simultaneous equation solution.
Right, right.
Thank you so much, sir.
Okay, so let me introduce the last gate that I would like to introduce for this single qubit gates right now. We might have few more gates down the line, but this is called a phase gate, and it has the symbol S, and it has this form 100I, because what it does, that it transforms 0 into 0, but for one state, it multiplies it with the, this iota. With iota is nothing but exponential iota pi by 2. So it means that if I talk about our general state cos theta by 2, 0, exponential iota phi sine theta by 2, 1. So with 1, it will add this iota, which is pi by 2. So it means phi goes to phi plus pi by 2. So this is a gate which adds a pi by 2 phase to angle phi. So it means that if we have a qubit, it rotates it by angle pi by 2 around z-axis. So because whatever the angle of this gate is, it adds pi by 2, so it rotates by 90 degrees. So this also means one thing, that now s power 4 should be identity, because once when I rotate something by 90 degree, to come back to the same state on a sphere, I will have to rotate it 4 times. And you can also check it by direct matrix multiplication, that you have to multiply this 4 times with each other, and then you get identity. Okay, so there's, by the way, a general phase gate as well. We can, let's say, have a symbol P. It's 1, 0, 0, exponential iota some phase phi. So this is a general phase gate, and this is also available, because this rotation around z-axis, I mean, the adding this phase phi to state 1, this can also be done very easily in hardware, because the pulse that is sent, it just have to have a phase in itself, which can easily be controlled by microwave generators that are sending pulses to the circuit. So this gate is also available in Qiskit very easily. We can add an arbitrary phase to our qubit. Okay, so any question or comment? Unfortunately, we couldn't go to multi-qubit gates today, that we will do in the next lecture. But right now, I want to introduce you how to implement these gates in using Qiskit in Jupyter notebooks. So if there are any questions about this single qubit gates, please go ahead. If not, I have prepared again a very simple and short notebook for today's session. And the idea is just to introduce you to how to implement these gates in Jupyter. What are the commands for that? So let me start sharing my computer screen now. We have this. So first of all, when I send you a notebook, you have to go to this upload button on your screen, and then you can go to the place where the notebook is saved, and you click this upload button. Yes, override, because I already have it here. So this is there. So this is the notebook in front of me. But if you want to create a new notebook, you can go to this button new, okay, and click Python 3. I have only Python 3 installed on my computer. Some people actually install more version of Python, those who have older notebooks and codes for Python 2, but we only have Python 3. So I click on Python 3 and I can open a new notebook as well. Anyway, so let me work with this new notebook. The starting point today is that
Sir, I'm sorry to interrupt. We can only see the command prompt. I'm not sure if you've already opened the notebook because.
Oh, okay. Can you? I think I shared only command prompt, unfortunately. Thank you for letting me know. Let me share the full screen. All right, okay. So here is the new notebook that I have created. So let's start from the simple command that from Qiskit, import quantum circuit. This execute I will not need. This air I will need. This air is a package that runs different quantum circuits. And then from visualization, I'm importing this plot histogram. So this is running. Okay, so let me take this code here and explain to you what are different commands. So first of all, you see that I'm importing numpy as np. This is a package that contains basic mathematical operations. And now I'm constructing a quantum circuit. So this is a command for quantum circuit. And then in the bracket, I have written 2 and 2. So this first two means the 2 qubits. The second two mean that 2 classical bits. So you can have a quantum circuit with only qubits, or you can have qubits and classical bits both. So qubits will have qubits and classical bits will have classical information. Now, the way it works in Python is this, that the things are labeled as 0, 1, 2, 3. So indexing start at 0. So this first command is qc.x, and in the bracket I have written 0. So first of all, remember Python is object-oriented based language. So almost everything is an object in Python. So when we have to perform an operation, whatever the thing that we are performing operation on, for example, this QC is a quantum circuit. This is an object that I'm performing operation on. So I will have to specify that object QC, and with dot, I will write the operation afterward. So this QC.x mean that the X gate is going to be applied on this QC, and it's going to be applied on the 0 bit. So similarly, just as an example, I'm applying this X gate on 1 bit as well. And then I have inserted this QC.barrier. This does nothing in quantum circuit, but this greatly helps in visualizing. We can arrange different parts of the program into different blocks. So this is a very useful visualization tool. But if you use it or not use it, that's your choice. Now the Hadamard gate is applied with this .8 symbol, and I'm applying it on a bit 0. And I also have a rotation around y axis gate. So this I didn't talk about when I was talking about gates, but general rotations around x, y, z gates axes are also available. You can have any rotation around any axis you want. Python has a gate to implement it. For example, I can have some angle np.pi by 3. So this is pi by 3. I'm using np because np is a numpy package, and pi is not available in Python as such. So I'm calling this pi from numpy package. Okay, so then this again Hadamard on bit 1, qubit 1, and then I'm again putting a barrier just for visualization. And now I'm putting a measurement operator on qubit 0, and I'm telling the program that measure qubit 0 and then transfer the information of measurement onto the classical bit 0. Similarly, there's a measurement applied to qubit 1, and the information of qubit 1's measurement is stored on the classical qubit 1. And at the end, I'm giving a command to draw this circuit. So let's see what it looks like. So this is a quantum circuit that is in front of you. So I have applied these X gates to both qubits. adamant gates to both qubits, then I have applied a rotation on y-axis. I can also have this rotation, let's say, around x-axis. Uh, and similarly rotation around z-axis rc. And then at the end, I have two measurements. So this is how we specify a quantum circuits using Qiskit. And let's see how do we run it. Next week, I will show you how to run it on IBM's quantum computers. But today and tomorrow, I will only be using the simulator, where we just simulate the effect of quantum computers. So, uh, so the way it works is this, that when we will be working on IBM's quantum computer, we will be writing that quantum computer here. But today, I'm just using a simulator. This is COSM quantum assembly simulator. So I'm specifying that from air is a package which has this simulator inside. So from this air, I'm getting this simulator, and they have used the simple backend because normally you will be using one of the quantum computers backend. So even for simulator, the command is still backend. And this simulator is then stored in this backend. And then this execute command, oh, I will need to call execute here, which I deleted. Okay. So now I'm going to execute this circuit, and the circuit that is to be executed is written QC, and then this backend specify what quantum computer I'm going to use. So in this case, it's only a simulator. So this backend comes here, and then I'm going to specify the number of shots, that how many times I have to run this quantum computer. Let's see if I just run it once. And then once it executes, it gives bunch of things. And from this execution, I'm just interested in results. So I get results. And even from results, I'm just interested in getting the counts of different measurement things. So when I execute and plot, you see on my output, I only get 1, which says that qubit 1 is one state and qubit 2 is in one state. And it is with probability 1, which is simply because I ran the circuit only once. So when I run a circuit only once, I will get only one output, even if my state is in some superposition state. At the end, after measurement, both of qubits would be in only one definite state. If I want to really understand what that superposition state is, I will have to run it many times. Let's say I run it 10 times. So now I see that I'm getting some distribution, that 0, 0 mean that qubit 0 is in 0 state, qubit 1 in 0 state. There's a 30% probability. Then qubit 0 in 0 state and qubit 1 in 1 state, 20%, and so on. But this might still not be true, right? 10 is not a really a great number of samples to guess the state. So let's run it for, let's say, 1,000 times. We are running it on some simulator, so it doesn't really matter. So it looks like that perhaps each state is 25% probability, and you see that's what it is approaching. So this is how we can, sort of run this circuit on this simulator, and almost in the same way we will be running it on a quantum computer. Let me just quickly show one more thing, and that is that okay, so let's say we open another. Okay, so anyway, I think that's enough for the single qubit simulations. The next part that I had dealt with the 2-qubit gates, but we will be talking about multi-qubit gates in the next lecture, and I will be, also discussing entanglement and teleportation in the next lecture. But any question about this running these circuits on notebooks, and or maybe what they do? So I see there's a question in the post I have to discuss. Okay. So Fatma, you can please stay on after this meeting ends. Okay, so if there are no questions or comments, I would like to thank you again for showing up today. And hopefully by tomorrow, we will be able to have a complete toolkit to start building some practical algorithms to do something. I will be sharing URLs of couple of reading materials that can help you, with the minor topics that we were not able to cover with this. But I think the best thing that you can do to learn it on your own is go to this website and you can almost see similar things that we covered in this lecture and many more that we have left out. And you can also learn from this website different commands for other quantum gates that we didn't cover. I was actually planning to share the notes that we work out during the class today, but unfortunately, most of today's notes have been lost. But last lecture's notes are there. So I'll try to save these notes periodically in future so that I will be able to share the PDFs of these class notes that we work out with you after the class. And I'll also be sending out this notebook that you can work with it yourself. Okay, so thank you, and let me stop